Take your seats, please. So welcome back to the UK Sea Ice meeting, which is embedded within some wider meeting that I'm not sure about. So to take us up to lunch, we have 4 speakers from some preeminent UK sea ice institutions. Starting off with Yevgeny from NOC in Southampton, who's going to gaze into his crystal ball and tell us about the future of waves. Apparently. Go ahead.
Thanks, Paul. So, can you hear me? Is that all right? Yeah. Okay. Good. Okay. Right. So, this is sort of a continuation of the previous talk to some extent. So, it's the same subject. It's wave sea ice interaction, and it's very similar model configurations I'm going to talk about. It's practically the realistic, so-called realistic ocean general circulation model. And it's realistic because we have a realistic topography, and we believe more or less realistic equations for the ocean and sea ice and boundary layer for the atmosphere to ocean interactions. So there's a quite long list of authors here, and that was a part of the European project called SWARP, which stands for the Ships and Waves Region Polar Regions, I think. And you can see several names of people actually present here in the audience. So Lucia Hosekova, she's currently at the University of Reading. Should be someone here. Stefanie with us in the NOC. Danny is here, and George Narser from NOC. He's not here. He's sort of tangentially involved. Tim Williams, the guy who developed the ice fragmentation model we are using, and Andrew Coward help us with modeling, and also Gurvan Madec, Nemo Guru, the guy who actually wrote more or less himself Nemo model, the Nemo ocean model. Right. Okay. So outline. I'll spend some time on motivation, and I'll describe the modeling system, and then I'll talk about the future plans, basically. Right, so motivation. So left sea ice from the 8th of September this year. It's not the recent picture, most recent, but it's quite recent. So one thing which is striking here, so we have the same situation as usual, which is on the right, when the Beaufort Sea is ice-free, basically, right? Which means large areas of the ocean are open to the action of wind, and you got waves there. That's main issue. Second issue, which is less obvious, if you look at the color scale here, and I'll try to show that, maybe, yeah, that's all here. That's basically this color scale. That's about 60% of ice concentration. So by definitions most of the people are using, this is MRZ type concentration, which means this is marginalized zone and there's some kind of loose ice, and as opposed to the compact ice for the ice pack. So the two features here, we potentially have waves and we potentially have a fragmented ice, basically. Right, so what is mean MRZ? So some kind of cartoon below showed this some kind of cross-section. To the right you have ocean waves, open ocean waves. To the left you have a pack ice, there is no waves there, only compact sea ice. In the middle it's something in between, basically. So you have a waves and you have ice. So that's called marginalized zone, and there's no clear definition in the classification of WMO, what is it is, but it says it's area between open ocean and ice pack, basically. And this is picture, I think it's Martin von Kopenau, that's actually MRZ. And you can see wave crest propagating to the ice area. Right. Another curious evidence came from rigorous stone paper, and they analyzed the satellite data from the infrared satellite, I believe, for the whole period of satellite era, 78 until 2012 for this case, and they look at the ice concentrations between 15% and 80%, which they classified as MRZ, and this is actually ocean. So the white bands here show this area which corresponds to this concentration range. And what happens if you look at the summer ice? This area is increasing in width and also increasing in size as well. So that's basically evidence that MRZ type ice cover is increasing for the last several decades. Now, and if you look at the what might happen, so this shows the high resolution projection we run with the coupled Nemo sea ice model, forced with the highly centered atmospheric model. So it's not fully coupled model, it's forced with the projected atmospheric fields, basically. And you can see that the loose ice concentration is expanding. And if you draw this 15% of ice concentration and 80% of ice concentration, that's your area of the future mist, basically. That's quite substantial. And if you do some kind of sums there, you see that actually that's a present period, and that's satellite picture from Regan Strand, basically. And you have some increase until mid-century, and there's very sharp increase in the fragmented ice area over the second half of the century. That's sort of motivation. And very briefly, because Stefanie mentioned that, yes, there's a quite substantial wave activity now in the Arctic Ocean. Extreme events, generally wave heights increasing. They increase by 30% in terms of significant wave heights. The satellite can put data on that. And the right one, again, it's a projection we run, and we sort of estimate wave heights from the wind, like Charnock relationship. It's very crude estimate, but they give us increase up to the 100% in some areas, basically, which is could be explained by the fact ice cover has retreated or became fragmented, basically. Right, so how it works actually. Okay, so if you're in the mist, again, background picture shows the mist. So you have waves propagating into this area. The waves fragment the ice, and at the same time they attenuate. They attenuated, so wave height became smaller. Wave period changed as well. And then this whole thing affects how ice behaves. So you have more fragmented ice, you have more less connected ice, you're actually reducing ice strength in a way. And it has impact on the rheology and also ice dynamics. And then it impacts ocean as well, because if ice moves differently, oceanic mixed layer moves differently, and then ocean underneath moves differently, basically. And there's a thermodynamical impact, which is here. So if you change the area of the open ice due to the waves, for example, the ice floes could bump each other, it's sort of drifting apart. In summer, you increase the area of the open water and insulation from sun and from atmosphere. So you change the heat content of the ocean, upper ocean. You change the ice, you start melting more sea ice, basically. And then that basically feeds back. So you're changing the distribution of flow sizes, and you're changing the conditions for sea ice, which attenuates wave, some kind of positive feedback, basically. Right, and what happens with the flow size? There's some kind of just general points for discussion. I know it has been discussed this week quite a lot. Yeah, so there's several processes which could affect fragmentation of ice. So surface waves breaking up, they break up ice that also are advected in the sea ice. Then the second part is melting of the ice flows from the sides. They change the concentration, also change the flow sizes. Those also freeze up of the leads, which change the distribution of flow sizes. And again, you need advection of flow size. If you want to describe the evolution of the flow size distribution, you need flow advection. And this sort of simplified equation show what happens. There's a tendency of the flow size distribution. It's very crude and simplistic, but that would have a source from waves, thermodynamics, collision due to the breakup of flows due to collision, and advection of the flow sizes. So in parallel, you need to address also the equation for the waves: wave advection, attenuation, and losses in wave energy due to interaction with ice flows, and also the nonlinear interactions. Right, so how it works for the so this is Steve Williams' model, and practically it's quite simple. If you get a plate, which is there, and the incident waves come to the area and start bending ice and breaking it, and you have two criteria to break ice. This is practically ice buckling in vertical plane, basically. So you have flexural stress criteria and also strain criteria, and you choose between two, some kind of probabilistic manner, and you arrive to some threshold when you could break the ice flows. And the interesting thing about it, so you break the ice into the flow sizes which have the wavelengths, basically. And it has been proven that initial breakup actually happened that way if you have a continuous ice plate. Now, and then you attenuate waves. So to the right, there's a table we are using from Alison Cahoot and Mellon, and that sort of tells you attenuation coefficient for different wave periods and different ice thicknesses. And also there's a dependency on the flow sizes, which is not actually here. And that's basically it. So that's some kind of model we are using. Right, results. So this is the global NEMO model integration with size at close degrees. So Arctic is roughly between 10 and 14 kilometer resolution, which is not too bad. And what we see here to the left, you see the maximum flow sizes from the wave breakup, and some kind of zoom, which is I just put in just to show you what happens in the area of the Greenland Sea, for example, in the area of Odin. So right now I'll show the significant wave height attenuation. Again, the clear attenuation in the ice age, very sharp one, where you have MIZ. And also you can see Odin as well. You can see that there's actually less wave energy in the Odin area as well. So there's a quite substantial relationship between the ice and the waves, basically. If you look at the Southern Ocean, actually, in fact, it's actually even more dramatic. So the waves in the Southern Ocean are very strong. You can see that, and probably we know why. And you see very strong gradients in terms of the significant wave heights between the open ocean and the ice-covered areas, basically. Right. Second part. So yes, that's wave breakup. Now, if you have a broken ice behaves differently. So the way how we tackle it, we practically implemented the combined rheology, and I explain what it is. So to the left again, this is the same picture of the MRZ, and it basically says yes, it's practically granular material basically. So you can model that probably as a granular material, but we are using continuum approximations. We need to do something about it. So what we did, we just followed one of this framework and introduced the pulsation to the mean ice drift velocity basically, and you split in these two, and practically you can play with the formalism used by most of the models, either VP or EVP models. So you could split the stress tensor into components, so-called frictional component, EVP, and collisional component, which is responsible for the collision of flows, and also have this effect of the flows basically colliding and drifting apart as well. So so Danny worked on this, and we practically using his formulation basically for that. And the beautiful thing in terms of the numerical model as I am basically, it could use the same code basically. You just could copy bits of the code, modify it, and that's you are basically. But there's a bit of differences here because there are several new parameters introduced. First of all, there's a parameter which is mean flow size introduced in the equations, and it's a kind of caliper. And secondly, more important, this is this GT parameter, which has a very unfortunate name, because when I say granular temperature, people ask, is it in kelvins? No, it's not. It's meter square per second square, basically. It's a specific kinetic energy, basically. So that's kinetic energy of the turbulent kinetic energy of the ice drift. That's this sort of additional component of the turbulent motion which we believe every flow has, basically. And if you do that, you arrive to the different formulations how you can solve it. So these are specifically the viscosities and also replacement pressure. So if you do that, and you need to solve the evolution equation for granular temperature, which is not that very difficult, but has some bits and pieces which are not trivial. So basically you have tendencies to the left, and you have a direction part, and also have a part which is diffusion part. And then you have different sources and sinks. So you have, for example, the sources due to the stresses between air and ocean, so it's like a turbulence pulsation of the currents and the atmospheric flow. You have sinks due to the internal stress and rubbing, and also have this term which is wave surge. So this is the fact that if you have waves, you have some kind of energy put in the ice flows when the waves moves for or a flow back and forth. It actually pushes it a little bit. Or it has also this turbulent component which is associated with that. So and then if you solve that, you get something like this. So that's a picture of the granular temperature or turbulent kinetic energy of the ice flows. And what is expected? Yes, you have a higher values around the marginal zone area where you have more influences of the collisional type of behavior, and that's fantastic as well. So this is much more pronounced. So that's some kind of framework. Now, a couple of results. Yes, there are some net effects. So you should distinguish between the effects of the implementing the breakup and the evolution of the flow size distribution. That's one effect. And second effect is due to rheology. So what we found so far, that actually rheological effect could be significant, but only in the very limited area around the ice edge and marginal zone. Whereas the flow size distribution effect has much wider geographical impact. And it's clear why, because if you start using size straight from the shelf, you have 300 meters flow size caliper basically, which is not right basically. So if you introduce more physical flow size caliper, it actually has impact on the ocean ice. So this picture shows the relative change in ice velocity, which means at point 1 this is 10%. Okay, so you have some changes which are around, well, about 8%, which does seem to be a lot, but actually it is, because if you think that this actually velocity goes into mixing, because if ice moves faster, the ocean moves faster. If ocean moves faster, you have a high vertical shear, and that leads to the high mixing basically. Yeah? And it has been mentioned by Stefanie and before that other people that the Arctic Ocean environment is very low mixing environment. So whatever mechanism is to actually increase mixing is very significant. So the second, and that's a plot basically shows some kind of order of magnitude of changes if you again have a breakup and rheology. So we're talking about the concentration changes around maybe 5%, 3%. Again, you have a large impacts in the MIS, small impacts in the pack ice. Thicknesses are about 5 to 10 centimeters, so it's not large. I think it's probably, we're talking about maybe about 10% of changes. But still, it within the range of the main processes we actually explored. And so if you look at the albedo changes, or look other mechanisms. That's probably the same rate of range of the change. Okay, right. To summarize, yeah, I tried to describe fundamentals, and I did say much about the oceanic impact because Stefanie talked about the mixed layer. We continue looking at the changes in the circulation. There are some changes in circulation, the state of the ocean, upper ocean, and what next? Well, we very keen to do the full coupling experiments. There are several projects try to target this, because if you have imposed wave fields and different mechanisms to actually reconcile the wave fields with the state of the ocean and sea ice, you're missing feedbacks. Most of the responses are related with the atmosphere, so most likely if there's a coupled system, these mechanisms will probably kick on much stronger, basically. That's one point. We're very keen to try this for the future. Didn't actually talk about the future much because we sort of did some experiments, but they're not very conclusive. So by introducing these approaches, most likely we will change the state of the ocean and sea ice in the future projections. Probably accelerate the ice decline, or most likely, but we can't try this. There's also theoretical development which we'd like to undertake, and there's several studies by Chris Howard and other guys looking at the combined thickness flow size evolution. This is the work with the University of Rheinland, and I think I'll probably stop here. Thank you.
Thank you, Yevgeny. Any questions for Yevgeny?
So if you go back to your slides where you show the effect on the thickness change, this one. The upper right, I'm trying to understand what you're showing here. You're showing that the wave interactions with ice in the central pack will decrease the thickness by 10 centimeters, but then you say that it's only confined to the marginal ice zone.
Yes, I said two things. One thing I said, yes, rheology, there's two effects here. Rheological, well, using different rheology leads to the changes in the marginalized zone. This is the total one. This is wave breakup and rheology, okay? So it changes the mean flow caliper. Instead of using 300 meters as standard in size, it uses the realistic one, or at least what we think more realistic. That's what it does, basically. So you're changing the flow size caliper, and if you're using standard lateral melting schemes, that will change your concentration and change your ice volumes, basically.
So that's exactly about the concentration. Yeah. The north of archipelago Greenland, all the way towards the North Pole, this is close to 100% for summer, and it's a thick ice.
Well, okay, so I think I don't know exactly. Okay, that's one thing. But we do have we see the impacts in the central park. It's not the major impacts, but we see impacts in the central park. We interpret this. It's because, as I say, you change. It's not only concentration change. Concentration is a part of the story. It's the fact that you change flow size, and yes, if you're in summer, that goes into the different melting, basically. If you're in summer, so that's summer, yeah.
That guy's flow sizes are not that good, right? Because we miss some processes that happen there.
That's true as well. So basically, that's a different issue slightly, because it's an argument whether this sensitivity is realistic and what causes it. So this sensitivity might be unrealistic because ice flows in the pack ice are too small. That's one possibility. And second question, what causes it? So I think currently our explanation that goes for the lateral melting alteration mechanism, basically.
This is reference to some simulation without those effects.
Yeah, that's a difference. Sorry, I didn't say that. That's a difference. There's a difference in ice concentration. It's a sensitivity run using breakup and rheology, less control run with the standard settings for size, basically.
And the NEMO having waves introduced under ice as well.
There's attenuation, there's a wave field which attenuated by ice, and also the wave advection into the ice as well, yes.
Okay.
So this is done.
Okay, I'm afraid we need to move on.
Yeah, okay.
Try and stay on schedule for lunch.